Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to cover the paper on learning to identify genders from raw speech signals using CNNs. This paper is by Selen Hande Kabil, Anna Amukahan, Matthew Megai Doss, and this paper is in collaboration with IDEAP Research and EPFL Lab. So the tutorial is going to cover the overview of the paper. Then we will see what is the proposed approach for gender identification. Then we'll see the data set used. Then we'll see experiments and result. Then we'll see what are the filter analysis they do in this paper. So the overview. So basically this paper is written for gender identification from audio. So basically you want to identify whether it's a male voice, female voice, just by listening to the voice. And this humans can do it very easily, as we know. And we want to develop an algorithm we want to develop an algorithm which analyzes the audio and tells whether it's a male voice or a female voice. And basically this paper uses raw audio signal processing directly instead of computing spectrograms, or instead of computing features like MFCC or fundamental frequencies. And they show that using direct raw audio gives you better results compared to using MFCC and fundamental frequency as input to any architecture, deep architecture. And they use the convolutional neural network to classify the audio into one of the gender, like male or female. And they show that they can feed a raw audio directly to a CNN, which is basically a one-dimensional convolutional neural network, which can learn some sort of features from the raw audio. And they use MLP, basically the multi-layer perceptron, to classify those features as, or they use that as a classification stage. And the dataset used is AV spoof and ASV spoof dataset. So basically AV spoof is audio visual spoof data, and ASV spoof is that the speaker verification spoofing dataset. And they at the end they show the results are better than normal MFCC based architectures. And they also show some filter analysis, or they show what are the kind of filters which these CNNs learn from the audio. So in the proposed approach, we have a feature learning phase or feature learning stage, where we use a one-dimensional convolution and max pooling layers to learn some features from the raw audio directly. And they have a classification stage where they use MLP and softmax to classify each segment of speech into one of the gender. And as you can see, the input system takes ST subscript T superscript C as a raw audio speech signal, which is basically a window which consists of one-dimensional speech signal with the context of C frames to left and right. And when you feed this segment, raw speech segment, into the model, you should be able to predict, or you should be able to give the probability score of basically, which should tell whether it's a male voice or a female voice, right? And that's the whole idea. I mean, the idea is simple. You just use raw audio as input to CNNs and MLP instead of feeding MFCC. And that's all they have done in this paper. Not not much fancy or different types of models they have added into this. So simple plain CNN, and the CNN will be able to process the raw audio, which is basically only CNN, which is being shown to give better performance for many tasks like speaker verification, language identification, and speaker identification. And in fact, the same guys have proposed raw audio based speaker verification from the same lab. Not sure whether the same people. So they have taken the raw audio network, which is the same sort of network, convolutional network, for speaker identification and verification, and they have showed it is much better than normal MFCC based ones. And the dataset used here is AV spoofing dataset, basically audiovisual spoofing dataset, and they have used automatic speaker verification spoofing dataset from 2015. And the data distributions like this. So they have AV spoof, audiovisual spoof data. In that they have a training with 14 speakers. 4 of them are female, 10 of them are male, and dev is 4 female and 10 male. and evaluation is 5 female and 11 male. And number of utterances, as you can see here. And in ASV spoof data, they have 20 speakers for training, which are female, and 15 male speaker for training. And number of utterances are, as you can see, 2000, around 2000 for female and 1500 for male. And in dev they have 7, and male they have 5. Basically the ASV spoof datasets don't have the evaluation, they don't have dev data. So what they do is they consider the dev data of ASV spoof as a evaluation data, and they split some of the training data itself for the dev. So as you can see here, right? So for the evaluation they have 26 speakers, which is basically the development data for ASV spoof, the original challenge, right? That is the data set being used. And coming to experiments, they have two baseline systems. A baseline system in the sense they want to show that this raw audio based processing models can give better performance. And for the baseline setup they have two baseline models. So one is which directly takes MFCC as an input to DNN, or normal neural network, and directly predicts whether it's a male voice or female voice. And another one which is again takes MFCC along with fundamental frequency as an input to the DNN and predicts whether it's a male voice or female voice. You can ask the question why they are using fundamental frequency as input, because humans or males will have low pitch compared to female voice. Basically what I'm meaning is the pitch of female voices will be more compared to the pitch of the male voice. So just by using frequency or fundamental frequency as an input, you will be able to classify whether it's a male voice or female voice, right? And that is what people have done in the past to classify the male and female voice, but it's not going to work that effectively. So they have to we have to develop a new algorithm which takes the full raw audio and learns some sort of new features which will predict basically whether it's male voice or female voice. That's one small feature, but there are other features also which are going to contribute to the discrimination of male and female voice. So we will see. And for this baselines, one uses MFCC and another uses MFCC plus the fundamental frequency. So for the MFCC calculation or capsular feature, we use HTK for as an input for HTK toolkit for extracting the capsular feature, and for fundamental frequency extraction features we use snack toolkit for fundamental frequency extraction. So they are using HTK for capsular MFCC and snack for fundamental frequency. And MFCCs are calculated over the frame size of 25 millisecond with a shift of 10 millisecond, and fundamental frequencies are calculated for 40 millisecond window with 10 millisecond shift. And they use QuickNet tool to train the deep neural network, and they are like one layer neural network with varying number of hidden layers, and they are taking the one which gives the best accuracy. And for the first baseline system, as I said, which takes only MFCC, they feed 38 dimensional MFCC feature with 4 left and 4 right context. So totally they get 342 dimension input as a input to the ANN1 system, which is one layer neural network which takes only MFCC. And a second baseline basically takes 38 dimensional MFCC features along with 1 dimensional fundamental frequency. So basically, as I said, over the window of 40 millisecond with a shift of 10 millisecond, they compute one pitch value for that particular window. So that way they get one more value along with this 38. So basically they get 39 values with 9 context windows. So basically they get 351 input features, and that they are going to feed it to NN2, which is basically a neural network with one layer hidden layer, and they are going to train it with QuickNet. And for the proposed system, basically, so when I say proposed system, the one which these guys are training, which is the raw audio based processing, basically which takes the raw audio directly as input to CNN along with multi-layer perceptron as the classification stage. So they take they use raw audio, but they do pre-processing just to remove the silent frames. So silent frames you can remove it using WAD, energy based WAD. The WAD detection. WAD is basically a active voice activity detection algorithm which removes the silence frames at the start and end of the speech sample. And that after that they also do some more pre-processing of standard normalizing the speech signal. Basically they remove the mean and remove the mean in the sense they subtract the mean of the audio and audio sequence, and then they divide it by the max value, so that they normalize it by the standard deviation. So that after they do the normalization, they feed that into one dimension CNN, which basically learns some features, and that goes as input to MLP, and then finally softmax. So coming to the results, so basically before results, let's see the architecture they use. Since the CNN and since they have a CNN along with DNN combination, they have to they have to create a network which is basically one optimal network. Optimal network in the sense the network which gives better accuracy. Since there are a lot of hyperparameters, for example, like number of CN, number of convolution layer, and width of kernels in each convolution layer, and number of hidden layers. So those are many hyperparameters that you have to take, and number of context also. So there are many hyperparameters you need to tune before you get an optimal architecture or optimal configuration of the network. So for that they are just using grid search, where they have the parameters, each parameter with range, like what is the range of this parameter can vary. So once they do a grid search on all this combination of all these parameters, then they get an optimal parameter. And the optimal parameter actually is this, I mean the one which they are saying it's going to perform well. Basically it's they have three different architecture, where one is one convolution layer, say another one is CNN2 refers to two convolution layer, and CNN3 refers to three convolution layer. So as you can see here, KW basically the window size, and DW basically shift of the kernel, and NF is number of kernels, and LR is learning rate. So these things, and you can see there are three convolution architecture. One CNN1 is a one layer CNN, one layer, and CNN2 is two CNN layers, and CNN3 is three CNN layers, as you can see here. Coming to the actual results, so basically they have, as I said, they have two baselines. So one is ANN1, which is basically takes MFCC directly as input, and ANN2, which basically takes MFCC plus fundamental frequency as the input. So on AV spoof dataset, they have 86% accuracy, and with ANN1 baseline, and with ANN2 they have 86.9% accuracy, and with ASV spoof they have 93 and 83 here, right? This is good, right? And so here they have done something interesting, where they train the architecture using AV train. AV train is basically audio visual spoof data, and they are testing it with ASV test. And you can see the degradation accuracy here. Basically it is going to go to like suddenly 88, 55% and 54%, and the same thing happens if you train the system using ASV data and test it with AV data. And I will tell you why this is happening later. And as you can see here, for any combination, or for any data, I mean for any model here, CNN1, CNN2, CNN3, basically these are the models which are proposed in this paper, are performing better than normal ANN1 and ANN2 baselines, right? But there is one interesting thing happening here, where the degradation is happening in this part, right? So this you have to explain. So basically here you are getting improvement over ANN1 and 2 baseline. Here also you are getting improvement, which is basically you can see you are almost getting 100% accuracy, 99.8, which is really good. And when you train with some data and test with some other data, actually you are getting some degradation, right? It is still good, 90% is still good. But if you see the last column here, they are training with ASV train, which is ASV spoof data, but testing with audiovisual or AV test data, you are actually getting degradation compared to baselines. So as you can see here, right? So basically they are degrading compared to normal normal baselines. Why this may be happening? Not sure. Even in the paper they say this may be happening because of mismatch in conditions, because ASV data is basically collected in anechoic chambers, which is like closed room where there is no noise, anything. but AV data is collected in real field, like in mobiles and all those. So there is a lot of mismatch in the data, one thing, and there is an insufficient number of speakers also. I mean, because this is not like 1,000, 2,000 number of speakers, it's just very small number of speakers. So maybe may not be generalizing to the model may not be generalizing to all other conditions. So that is the reason, maybe the model is not performing even compared to baseline. You can see it's like almost 50% degradation, like from 80 to 39. It's really bad. And at the end we see some frequency analysis. So basically they have plotted the frequency response, cumulative frequency response of the filters in the CNN2 and CNN3. So the top one is the cumulative frequency response of the CNN2 architecture. Basically there are two CNNs, and CNN3 cumulative frequency response is this, and this is done on AV spoof data. And another one is they also found out that average filter frequency response of 30 millisecond speech of the phoneme E uttered by a male speaker looks like this, the frequency response, and this is for CNN2 and this is for CNN3. But interesting thing you can see here, for a female voice, basically your formant frequencies are very high here, which you can see that which basically tells you like females have very high pitch, right? So and it's for the same phoneme, it's the same phoneme E, and here also it's he, but you can see the frequency response is almost flat after high frequency. But for female voice, the frequency response is really like peaky at after frequency from, let's say, 2K, right? So this is very interesting, and this is for CNN2 and this is for CNN3. And thank you so much for watching this video. If you are not subscribed to my channel, please subscribe, and like my videos for more content. Thank you.